Welcome to Mech Cosmos, Engineering, Explained. On the evening of April 20, 2010, the Deepwater Horizon oil rig was 77 kilometers off the coast of Louisiana in the Gulf of Mexico. It was drilling one of the deepest oil wells ever attempted, the Macondo well, at a water depth of 1,500 meters, with a total well depth of nearly 6,000 meters below the seabed. On board were 126 workers. The rig had just completed 87 consecutive days without a safety incident. BP, the company that owned the well, was preparing to temporarily seal the well and move the rig to its next location. The project was already 43 days behind schedule and significantly over budget. There was pressure to finish quickly and move on. At 21:49 that evening, a surge of natural gas shot up through the drill pipe, bypassed the last line of defense, and ignited on the drill floor. Two explosions tore through the rig within seconds. Fires erupted across the platform. The crew had no warning. 11 workers died in the initial explosions. 17 more were seriously injured. The remaining workers abandoned the burning rig. Deepwater Horizon burned for 36 hours before sinking to the ocean floor 1,500 meters below. But the disaster had only just begun. The well was still open. Oil and gas were escaping from the Macondo reservoir at the bottom of the ocean at rates that would eventually reach 62,000 barrels per day. For 87 days, the world watched helplessly as crude oil gushed into the Gulf of Mexico. By the time the well was finally sealed on July 15, 2010, approximately 4.9 million barrels of oil, over 780 million liters, had been released into the ocean. It was and remains the largest accidental marine oil spill in history. The environmental damage to the Gulf of Mexico was catastrophic, and some of its effects persist to this day. This is the complete engineering and human factors explanation of the Deepwater Horizon disaster. We are Mech Cosmos, Engineering, Explained. Let us begin. To understand what happened at Deepwater Horizon, you first need to understand the engineering of deepwater oil drilling and the specific challenges of the Macondo well. Deepwater Horizon was a semi-submersible drilling rig, a type of offshore platform that floats on the ocean surface supported by large pontoons partially submerged below the waterline. The semi-submersible design provides stability in rough seas by positioning the main buoyancy below the wave action zone. The rig was held in position over the wellhead on the ocean floor by a dynamic positioning system, a sophisticated computer-controlled system of thrusters that continuously adjusted to maintain the rig's position against wind currents and waves without the need for anchors in the deep water. The drilling operation worked by rotating a drill string, a series of connected steel pipes, from the surface down through 1,500 meters of water and then into the seabed. The drill bit at the bottom of the string cut through the rock. Drilling mud, a carefully engineered mixture of water clay and chemical additives, was continuously pumped down through the center of the drill string and returned up the annulus between the drill string and the wellbore wall. The drilling mud served multiple critical functions. It cooled and lubricated the drill bit. It carried the rock cuttings from the bit back to the surface. And most importantly, it provided the hydrostatic pressure needed to control the well. The weight of the column of drilling mud in the wellbore exerted a downward pressure that counteracted the upward pressure of the oil and gas in the reservoir. Maintaining this pressure balance was the fundamental safety requirement of the entire drilling operation. The Macondo reservoir was an abnormally high pressure formation. The pressure of the oil and gas in the reservoir was significantly higher than normal for its depth. This made it a technically challenging well to drill safely. Throughout the drilling operation, the crew had to carefully manage the weight and composition of the drilling mud to maintain the pressure balance and prevent the reservoir fluids from flowing upward into the wellbore, a condition called a kick. If a kick was not detected and controlled quickly, it could escalate into a blowout, an uncontrolled flow of oil and gas from the well. The last line of defense against a blowout was the Blowout Preventer, the BOP. The BOP was a massive stack of hydraulic valves mounted on the wellhead on the ocean floor. It weighed approximately 300 tons and stood nearly 18 meters tall. The BOP contained multiple redundant valve systems designed to seal the well in an emergency. The most critical component was the blind shear rams, two hydraulically powered blades that were designed to cut through the drill pipe and seal the well completely even if the drill string was in the hole. The BOP was the ultimate safety device, the last resort that would prevent a blowout from becoming a catastrophe even if everything else failed. In the final days before the accident, a series of decisions were made that compromised the safety of the well. The cement job, the process of pumping cement down the well to permanently seal the production casing in place and create a barrier against reservoir fluids, was completed on April 19th. Halliburton performed the cementing operation. The cement used was a nitrogen foam cement that had shown signs of instability in pre-job laboratory testing. Despite these warning signs, the cement job proceeded. The number of centralizers used to center the casing in the well bore, critical for ensuring the cement flowed uniformly around the entire circumference of the casing, was reduced from the recommended 21 to just 6 due to concerns about the time and cost of obtaining additional centralizers. BP's own engineers had warned in an email that using fewer centralizers risked a poor cement job and a significantly increased risk of a gas flow problem. The warning was noted and ignored. On the morning of April 20th, the crew conducted a negative pressure test, a procedure designed to verify that the well barriers were sound and that the well could be safely temporarily abandoned. The test involved reducing the pressure in the well bore below the reservoir pressure and observing whether oil and gas flowed into the well bore, indicating a barrier failure. The results of the negative pressure test were anomalous. Pressure readings were inconsistent and difficult to explain. The well was showing signs that the cement barriers were not holding. However, the crew, under pressure to complete the well and move on, misinterpreted the anomalous readings. They convinced themselves that the results were acceptable and that the well was secure. They were wrong. At approximately 21 SAO on April 20th, reservoir fluids began flowing into the wellbore. A kick had begun. The flow was not immediately detected. The drilling mud level in the mud pits, which would normally fall as reservoir fluids replaced the mud in the wellbore, was not being closely monitored at the critical moment. By the time the kick was recognized, the well was already flowing strongly. The crew attempted to activate the BOP and divert the flow, but events moved too quickly. A massive surge of natural gas shot up through the drill string and erupted onto the drill floor. The gas cloud ignited. The two explosions followed within seconds. The BOP failed to seal the well. The blind shear rams, which should have cut the drill pipe and sealed the well, did not function as designed. Investigation later revealed multiple problems with the BOP. The hydraulic system that powered the shear rams had insufficient pressure to cut through the drill pipe at the location where the pipe was positioned at the moment of the blowout. The drill pipe had buckled under the extreme conditions and was not centered in the BOP. The shear rams could not cut through it effectively. The BOP had also not been properly maintained and had known defects that had not been repaired. The last line of defense, the device that was supposed to make a catastrophic blowout impossible, failed completely. For 87 days, BP and its contractors attempted to stop the flow. Initial attempts to close the well using remotely operated vehicles failed. A large containment dome lowered over the wellhead became clogged with methane hydrates, ice-like crystals that formed when the cold, deep water combined with the natural gas. A smaller containment cap had limited success capturing some of the oil flow, but much continued to escape. A relief well, the definitive solution, was being drilled simultaneously but would take months to complete. Ultimately, a tighter-fitting containment cap installed on July 12th stopped most of the flow, and the relief well intercepted the Macondo Reservoir on September 17, 2010, allowing the well to be permanently killed with heavy drilling mud and cement. The investigation into the Deepwater Horizon disaster identified a comprehensive failure of safety systems management and decision-making at every level. The Presidential Commission appointed to investigate the disaster found that the accident was not the result of a single catastrophic failure, but of a series of poor decisions and missed warning signs stretching back months before the accident. BP, Halliburton, and Transocean, the three companies primarily responsible for the well, all shared responsibility for the decisions that led to the disaster. The cement job was identified as the initiating cause. The unstable nitrogen foam cement failed to provide an effective barrier against the reservoir fluids. The decision to use fewer centralizers than recommended contributed to the poor cement quality. The decision not to run a cement bond log, a diagnostic test that would have evaluated the quality of the cement job, meant that the barrier failure was not detected before the well was temporarily abandoned. The misinterpretation of the negative pressure test was identified as the critical missed opportunity to prevent the disaster. If the anomalous pressure readings had been correctly interpreted as evidence of a barrier failure, the well would have been shut in and the cement job remediated before the blowout occurred. Multiple engineers and managers had the information needed to recognize the danger. None of them did. The failure of the BOP was identified as a fundamental problem with the regulatory framework governing offshore drilling. The BOP had been certified as functional, but the certification process was inadequate. The device had known defects. The maintenance records were incomplete. The testing procedures did not adequately verify that the shear rams would function under the actual conditions of a blowout at depth. The regulatory agency responsible for overseeing offshore drilling, the Minerals Management Service, was found to have had an inappropriately close relationship with the industry it regulated and had failed to maintain adequate independent oversight of safety-critical systems. The consequences of the Deepwater Horizon disaster were far-reaching. The environmental damage to the Gulf of Mexico was immense. Approximately 1,770 kilometers of coastline were oiled. Fisheries were closed across a vast area of the Gulf. Marine mammals, sea turtles, and seabirds died in large numbers. The long-term ecological effects continue to be studied more than a decade later. BP ultimately paid over $65 billion in cleanup costs, fines, and settlements, the largest corporate settlement in American history at the time. The disaster triggered a comprehensive reform of offshore drilling safety regulation in the United States. The Minerals Management Service was abolished and replaced by three separate agencies with clearer mandates and stronger independence from the industry. New regulations required improvements to BOP design and testing standards. Control training requirements for offshore workers were strengthened. The use of independent third-party verification of safety-critical decisions was mandated. These reforms have made offshore drilling significantly safer, but the fundamental challenges of operating in deep water under extreme pressures with complex geological conditions remain. The Deepwater Horizon disaster is the definitive case study in the catastrophic consequences of allowing schedule pressure and cost considerations to override safety judgment in a high-risk engineering environment. Every decision that contributed to the disaster, the reduced number of centralizers, the unstable cement, the misinterpreted pressure test, the inadequately maintained BOP, was made in an environment where the pressure to complete the well quickly and move on was palpable. The engineers and managers involved were not malicious. They were experienced professionals operating under organizational pressure who made a series of decisions that each seemed reasonable in isolation, but that together created the conditions for catastrophe. That is the lesson of Deepwater Horizon. That is why we study these disasters, not to assign blame, but to understand exactly what went wrong so that we can build the systems, cultures, and regulations that make similar catastrophes less likely in the future. We are Mech Cosmos. Engineering. Explained. If this video gave you a deeper understanding of what happened at Deepwater Horizon and why, then subscribe, hit the notification bell, and join us for the next video, because every machine has a story, and sometimes that story teaches us how to make the world safer.